Year 13, Lesson 2, Sequences and Series. So in this lesson, we're going to focus very specifically on a type of sequence which is known as an arithmetic sequence. I'm going to write down two very simple examples of arithmetic sequences. So the first one, 2, 5, 8, 11, 14. And the second one, 12, 10, 8, 6, 4. Now, what do you notice about both these sequences? Because they have something in common with each other. Yep, you can see, hopefully, that in each case, the terms in the sequence are separated by the same difference. In the first sequence, each term goes up by 3 each time. So you add 3 to the previous term to generate the next term. In the second sequence, there is a gap of -2 between the terms, so you subtract 2 to generate the next term. And that's what creates an arithmetic sequence, which you may also previously have called a linear sequence. Now, some new pieces of vocabulary to introduce here. Arithmetic sequences are sometimes also called arithmetic progressions, and you must get used to that word progression. You will see it in the textbook quite a lot and in exam papers. Now, the amount by which the terms go up or down are called the common differences. So we have a common difference of 3 in the first example and a common difference of -2 in the second example. And a sequence is arithmetic if it has a constant common difference. So what we're going to explore now is whether we can identify a rule which will help us find the general term for any arithmetic sequence. Now, we can do this for specific sequences very easily, and you've been doing this going all the way back since year 7. So, for instance, if you were asked to find a general formula for this sequence here, well, you can see that the gaps between terms are 3. So this is going to be based on 3n or 3k, depending on which variable you want to use. 3 times 1 is 3, but the first term is 2, so let's subtract 1. Check that with the second term. 3 times 2 is 6, subtract 1 gives you 5, which is the second term. So we could write ak equals 3k minus 1, and that gives us a general rule which will generate any term in that sequence. We could write an equals 3n minus 1 as well. It doesn't really matter. But what we want to try and do is aim to do this for any arithmetic progression or arithmetic sequence. So A1, the first term, is A. Now A2, the second term, will be generated by adding the common difference to the first term. So we simply add D and we generate the second term. Now A3, the next term, will be generated by adding D to the previous term, which gives us 2D. We can then generate the next term, A4, which is A plus 3D, and so on and so forth. Now, look at the pattern here. And you will hopefully start to see how the rule could take shape. So if we have AK, this would equal A plus K minus 1 multiplied by D. And that is a very important formula for the general term of an arithmetic progression. So we have a formula which will generate any term in a sequence. Now, sometimes when we're dealing with a finite sequence, some textbooks will refer to there being n terms, and this means that an is the last term, which is also called L, which we might write as a plus n minus 1 D. This isn't something you should really worry about too much. It is sometimes a little bit of excessive notation that you find in the textbook. You really need to just remember that the general formula is a plus n minus 1 multiplied by the common difference when you're dealing with the nth term, or a plus k minus 1. It really doesn't matter whether you're using k or n. I've used both of these examples because you will see both in the textbook, but later on when we do examples you will see that I tend to use this as the general formula using n rather than k. So let's see whether this would have worked with the sequence we started off with as our example at the top of the screen. So we can see in this example over here that a is equal to 2 and d is equal to 3. So we could say that ak is equal to 2 plus k minus 1 multiplied by 3. And then if I expand that bracket, that gives me the following, which simplifies down to give me 3k minus 1, the same formula as up here. Now you may be asking, why is there value in generating this result down here when it's so simple to find the general formula for a sequence like this? Well, the answer to that question is in year 7 you might have been asked to find the general formula for a simple linear sequence like this, but at A-level the questions will be by far more complex. They will involve detailed problems in which it is very, very much simpler to know this result here. It's very rare that you would be given a sequence like 2, 5, 8, 11 and asked to find a formula for the nth term. You're much more likely to get more complex algebraic sequences, and we'll be starting to look at a few problems shortly. So let's look at an example, an arithmetic sequence. So let's take a look at this example. Read the question carefully. We are given an arithmetic sequence. We are told that the first term is 5, a equals 5, and we have a common difference of 4. So as you find this information out, write it down. One of the terms in the sequence is 149. What is the position of this term in the sequence? So we know that AK equals A plus K minus 1D, or if you like, AN equals A plus N minus 1D. It really doesn't matter. So we know that a particular term is 149, but we don't know what the K value is, i.e. the position in the sequence. So let's just sub into this formula. 149 is equal to A, which is 5, plus K minus 1 multiplied by the common difference of 4. And as you will see, you now have a very, very simple linear equation to try and solve. So 149 equals 5 plus 4k minus 4. 149 equals 1 plus 4k. 4k is equal to 148, and k is equal to 37. Now, you can see straight away here, this is by far more complex than problems you would have seen at GCSE or Key Stage 3 involving linear sequences. You need to know how to use this formula, and you need to know that this formula exists. You wouldn't really be able to answer this question very easily otherwise. So we're now going to progress to have a look at arithmetic series. This is when we add together the terms of an arithmetic sequence together. So let's start with a simple example. So our aim is to find the sum of the terms in this arithmetic sequence. So far we still have a sequence. If we want to turn it into a series, we have to add all the terms together. So the question is asking us to add 5, 10, 15, 20, and all the subsequent multiples of 5 until we get to 100. Now, we could go about this by simply inputting the values into our calculator. It's not a particularly difficult question, but that's a very unsophisticated approach. What we're going to aim to do is see if we can find a shortcut which will allow us to find the sum of these terms very quickly, and we're then going to see if we can generalise that. So here's what we can do. I'm going to write out the same series, but I'm going to write it out backwards. So I'm going to write out 100 plus 95 plus 90 plus 85 plus all of the other multiples of 5 down to the first one, which is 5. So it's the same series, I've just reversed the order. Now, here's a very nice trick. We're going to add together all of the terms pairwise in these two series. So I'm going to add together 5 and 100, 10 and 95, 15 and 90, and so on and so forth. I'm adding the first terms together, the second terms, the third terms, so on and so forth. So that's 105, 105, 105. All of the pairs add up to 105. Now, this makes life a lot easier because if we know how many terms there are, then we know that the pairs all add up to 105, so we can multiply the number of terms by 105. Now, 100 divided by 5 is 20, so there are 20 terms in total. This is the first pair, second pair, third pair, fourth pair, ... all the way up to the 20th pair over here. So there are 20 pairs. Each pair add up to make 105. Now, if I work out 20 times 105, that gives me, so this is 2,100. But of course, we've added everything twice because we added all of these terms and all of these terms as well. We've included 2 of the series. So we could say 2 multiplied by the series total equals 2,100. So if I want to work out the series total, that's 2,100 divided by 2, which of course comes to 1,050. So the total of the numbers, 5 plus 10, etc., all the way up to 100, works out to be 1,050 using this little trick. Now, this little technique is attributed to a mathematician named Carl Gauss, who was a really very eminent mathematician. So you may want to look up the story of him being asked to add together the first 100 numbers in class and being able to do it very, very quickly to the surprise of his maths teacher because he worked out this trick. So what are we going to do now? We are going to aim to generalise this. So our aim is to find a formula which will allow us to add together as many terms as we want to in any arithmetic series. So our first job is to write down our arithmetic series. Now, my first term is, of course, A. My next term is A plus D. My next term after that is A plus 2D, and so on and so forth. Now, I'm adding these terms together because that's what creates a series, and I'm going to carry on until I get to the very last term, which I will call A plus n minus 1d. So I'm basically saying there are n terms in my series. Now, it might be quite nice to fill in the term before the last term, which would be A plus n minus 2d. I'm going to put in some brackets. They're completely meaningless because we're adding here, but it might just help you distinguish each term in the series. Now, I'm going to call the total of the terms capital S. Be careful with your letter there, that's an S, not a 5. And we've established that there are n terms in my series. So this S here refers to the sum of n terms. So what did we do last time? We wrote out the series again, but we wrote it back to front. So I'm still going to write out S, but I'm going to reverse the order of everything. So I'm going to write the last term first. So if you recall, that's A plus n minus 1d. And then the previous term was A plus n minus 2d. And if you want to write out the term before that one, that would be A plus n minus 3d, and so on and so forth. Now, the very first term should go here, and then the second term, which is a plus d, should go here. So I've just written out the same series, but I've written it out backwards like we did last time. Again, I'm going to put in these yellow brackets, which have absolutely no mathematical value here, but they do sometimes provide a little bit of clarity so you can see which term is which. Now, what did we do last time? We added the two series together. Remember, they represent exactly the same thing, just written in two different orders. So this is what we're going to do. We're going to add together vertically through the pairs. So this will mean we end up with two lots of s on the left-hand side. What will we end up with on the right-hand side? Well, it's actually very easy to see as we look through the terms. If we add these two together, you can see straight away you'll get 2a plus n minus 1d. And if you look at the last pair over here, which are of course exactly the same as the first pair, you'll get 2a plus n minus 1d as well. Now, is that true of all the other pairs as well? Yes, it is. So for instance here, if we're adding these two together, I'll just simplify the lower example and expand the brackets here. So that's a plus nd minus 2d. And you can see when you add these together, that will give you 2a plus nd minus d, and hopefully you can see that if you factorise out the d from this part over here, this will give you 2a plus n minus 1d. And that's true of every pair throughout. So we know that this pair here is the same as the pair we've just added together, so that will also be 2a plus n minus 1d. And you can check that for any other terms you want to. So for instance, we'll just check it for one last pair. So I'll expand the brackets here again in the second one, in the lower one, a plus nd minus 3d. Now if you add together this and this, you should be able to see straight away you get 2a plus nd minus d. And again, that will give you the same result that we've got each time. So this is what we have. We have 2s equals the same result added together n times. Remember, there are n terms in this series. So we can simplify the right-hand side by saying we have n lots of 2a plus n minus 1d. But like last time, we don't want 2s. We don't want 2 times the sum of the n terms. We want to know what s is. So we simply divide by 2. So we would write s, the sum of n terms, is a half n to a plus n minus 1 multiplied by d. I've tried to bring a little bit of clarity here by writing different parts of this in different colours. Now, this is a really important formula. This is the sum of n terms of an arithmetic sequence or an arithmetic progression, where the total sum of the terms is half of n, where n is the number of terms, multiplied by 2a, where 2a is the first term, plus n minus 1 multiplied by d, where d is the common difference. Now, let's see if this works with the example we were looking at earlier on. If you recall, we added together 5 plus 10 plus 15 all the way up to 100, and we got a total of 1050. So a is equal to 5, d is equal to 5 as well, n is equal to 20, remember it's the number of terms, and we know from our formula that s, the sum of n terms, is equal to a half n 2a plus n minus 1 multiplied by d. So that's a half multiplied by 20. 2a is 10 plus 19 multiplied by 5. And you can input all of this into your calculator and you will find that you get the total of 1050. So let's quickly summarise the formulae that we have just come up with. So AK equals A plus K minus 1D is a formula which will allow you to work out any term in an arithmetic progression, or an AP as we call it for short. Now, if you want to add together n terms in an arithmetic progression, we have S, which is equal to a half n 2a plus n minus 1d. So that's the sum of n terms in an arithmetic progression. Now, there is one slightly different version of this second formula that we're just going to briefly look at. So if I take part of this on the right-hand side, and if I just write it out as a plus n minus 1d, so hopefully you can see all I've done is split up the 2a into an a plus a. Now, you may recognise that earlier on we sometimes say that a plus n minus 1d is the last term, which we call L. So this then gives us the result S equals a half n a plus L, where this is just another version of the sum of n terms. It can be quite useful if you are given the first term, which of course is A, the last term, which of course is L, and obviously you also have to know the number of terms n in order for this to work. So you will see a lot of these formulae, especially this one here and this one here, and we may also at some point make use of this one here. So we're going to finish off by seeing how we can apply this to a series of more complex problems. Let's read through the first example. A person saves money each year. They start with an initial investment of £5,000. In the following year, they invest £6,000, then £7,000, so that each year the amount invested increases by £1,000. So what they're saying here is that A, or A1, equals 5,000. A2, the second term, is equal to £6,000. A3 is equal to £7,000. So each year, an extra £1,000 on top of the previous amount invested is then invested. So year one, we invest £5,000. Year two, we add another £6,000 into the account, then £7,000, etc. So how much is saved in the 8th year? So remember our formula, AK equals A plus K minus 1 multiplied by D. So A is equal to 5,000. Now we're looking at the 8th year, so that's A8. So that's 8 take away 1 or 7 multiplied by the common difference, which is £1,000. So that then simplifies to give us £12,000 saved in the 8th year. Now, the second question is a little bit different. How much money has been saved in total by the 8th year? So this time they're asking us to find the sum of the amounts. So they're effectively asking us to do 5,000 plus 6,000 plus 7,000 all the way up to the amount saved in the 8th year, which is 12,000. Now, yes, you could write them all out and add them up on your calculator, but we're going to be more sophisticated than that. We're going to use the formula S equals a half n 2a plus n minus 1d for the sum of the terms of the arithmetic progression. So here you can see the arithmetic series. We're adding the terms together. Now, we know that A is 5,000. We know that D is 1,000. We know that N is equal to 8. And we have all the information. So that's a half multiplied by 8. 2A plus n minus 1, 7, multiplied by 1,000. So substitute all of this into your calculator, and this gives us £68,000. Now, if you wanted to, you could use that alternative formula that we looked at. Remember, S equals a half n a plus l, seeing as we know the last term. So that's a half times 8 multiplied by 5,000 plus 12,000. And then input that into your calculator and you will find you also get £68,000 again. So let's look at a slightly more complex problem. Think about all the key words as you work through this. An arithmetic progression has 10th term 11.1 and 50th term 7.1. We need to find the first term and the common difference. We also need to find the sum of the first 50 terms of the progression. Right, I think we need to summarise all the information we have. So A10 equals 11.1. A50 equals 7.1, and we need to find A, find D, and then we need to find what we call S with a little subscript 50, which means the sum of the first 50 terms of the progression. Now, I'm going to use that general formula, AK equals A plus K minus 1D, to convert this information into something a little bit more meaningful algebraically. So let's start with the 10th term, which is 11.1. So 11.1 is my term, and that equals A, which I don't know, plus K minus 1. Well, K is equal to 10 in this instance, so that's 9D. I'll do the same with A50, the 50th term. So 7.1 equals A plus 49D. So I'm basically using this result over here and filling in the information I can. So you can see straight away I have a pair of simultaneous equations. A plus 49D equals 7.1. A plus 9D equals 11.1. We're going to subtract, which gives me 40D is equal to negative 4. So D is equal to negative 1/10. Or negative 0.1. You can then substitute that back into an equation of your choice. I think we'll substitute back into equation 1, and then we can very simply work out what A is equal to. So A is equal to 12. Now, a number of you would be saying, why can't we just do 7.1, take away 11.1, and then divide by the correct number? Well, you can do. There is a good chance you may get it wrong because you're not writing down where you're working, and fundamentally you're not using the sophisticated techniques that you've learnt. You're trying to hold on to some very basic maths there, and you need to move on. When questions become more complex than this, when questions become more algebraic, you will not be able to solve them unless you understand and make use effectively of the formulae that we have introduced. So don't just try and use basic addition, subtraction sort of calculations to try and work out these problems. You've got to force yourself to be more sophisticated than that. Otherwise, you're not going to take on the high level of knowledge that you need at A level. Now, the last part of this wanted us to work out the sum of the first 50 terms. So remember the formula, S equals a half n 2a plus n minus 1 multiplied by d. Now, n is equal to 50 in this case. We've worked out that a is 12 and d is negative 0.1. So all that remains is for us to substitute in this information and go from there. So input this into your calculator and you should get an answer of 477.5. So, a slightly wordier example in number 3. In a quiz game, contestants get £10 for answering the first question correctly, then a further 20 for the second question and a further 30 for the third, and so on until they get a question wrong and are out of the game. So, Haroon answers 6 questions correctly, show that he receives a total of £210. So, notice it's referring to the total amount that he gets. So what do we know? Well, A, the first term, is £10, so that's A1, or A. A2 is 20, A3 is 30, and so on. So the common difference, D, is equal to £10. Now, he answers 6 questions correctly. We're not just looking for the 6th term, okay? We're trying to add together the amounts he gets for the first 6 questions. So the formula we need is S equals a half n 2a plus n minus 1d. We want the total, not just the actual amount he gets for the 6th question. It's the amount he gets for all the previous questions as well, added together. So n is equal to 6. So this is 3 multiplied by 20 plus 5 multiplied by 10 over there. So that's 3 multiplied by 70, which gives us the £210 for the question. Part B. State in a simple form a formula for the total amount received by a contestant who answers n questions correctly. So again, we're looking at the total amount. So S equals a half n. Now, we can fill in our formula, which I've got written up here, the value of 2a, because a is equal to 10, so that's 20, plus n minus 1 multiplied by d. And again, we know that d is equal to 10, so I can simply say multiply by 10 here. Now I can simplify my algebra a little bit here, so that's half n, 20 plus 10n minus 10, and I can simplify further, a half n, 10 plus 10n, and I can, one last step, I'll multiply everything in the brackets by a half, so that's n, 5 plus 5n. Now if you wanted to, you can expand or you can pull the 5 out at the front, so s equals 5n, 1 plus n to finish off. Now there is one last part to this question. Hence find the value of n for a contestant who receives £10,350 from this game. So what do we know? Well, we know that the formula we've just found, which is 5n, 1 plus n, represents the total amount that has been won. Now, we are being told that this is equal to 10,350, and we have to find the value of n. So we have a very simple equation to deal with. Let's divide both sides by 5, which gives us n. 1 plus n equals 2070. Expand the brackets, so we have n squared plus n equals 2070, and of course we have a quadratic equation. Now I would input this into your calculator to solve, and you will find it factorises as n minus 45, n plus 46 equals 0, which gives us algebraic answers of n equals 45 and n equals negative 46. But of course, we reject the second answer, as n is the number of terms. It cannot be negative. So this means that the number of terms, n equals 45, is the final answer. Right, example 4. The nth term of an arithmetic progression is 6 plus 5n. Find the sum of the first 20 terms. So, an equals 6 plus 5n. Now we could have said ak equals 6 plus 5k. Just go with the notation that's been given in the question. What can we do with this? Well, we can find out the first term by substituting n equals 1 in. So this tells me that a1 is equal to 11. Now this is equal to a, which will be very useful when we're substituting into this formula here and we want to find out the sum of the terms. We're going to need to know what a is equal to. Now, if I substitute in n equals 2, this tells me that a2 is equal to 6 plus 10, which is equal to 16. And of course, that's a plus d, the second term. So it's very obvious from here that the second term d has got to equal 5, the difference between the two terms. So if I'm now going to calculate the sum of the first 20 terms, and I might refer to that as S20, that's a half of 20, because n is equal to 20. 2 lots of a, which is 22, plus n minus 1, which is 19, multiplied by d, which is 5. Input that straight into your calculator, and you get an answer of 1,170. And the last example here, we are looking at an arithmetic progression. The second term is 11, so that tells you that a plus d equals 11, and the sum of the first 40 terms is 3,030. We've got to find the first term and the common difference, so we need to find a and d. Now this is interesting. The sum of the first 40 terms is 3,030. So remember, the sum of n terms is a half n 2a plus n minus 1d. So that tells us that 3,030 is a half of n is 40, so that's 20. 2a, we don't know the value of a, plus n minus 1, which is 39d. So we have a pair of simultaneous equations. Here they are, here and here. But I think we're going to do a little bit of tidying on the second equation, before we actually look at solving them. So I'm going to divide both sides by 20 first of all. So that gives me 151.5 equals 2a plus 39d, and we'll call that equation 1, and then we've got equation 2 over here. Now there are so many different ways of solving simultaneous equations. We'll do a slightly different way to the previous method. I'm going to rearrange the second equation so that it tells me that a is equal to 11 subtract d. I'm going to substitute this into equation 1. So this tells me 151.5 equals 2 lots of 11 minus d plus 39d. Now you have a very basic linear equation to solve here. So what does this give us? 129.5 is equal to 37d, so d is then equal to 3.5. And a, we can substitute back into a equals 11 minus d to work out that a is 7.5. Again, hopefully you can see that it would be very, very difficult, if not impossible, to solve these problems without solid knowledge of the formula which gives you the general term of an arithmetic sequence and the formula which allows you to find the sum of the terms in an arithmetic series. You must make sure that you know both these formulas, you know how to use them, and that you know which formula should be used in which situation when you're solving problems.